In this video, we're going to be discussing grain size distribution and how to determine a grain size distribution chart or graph. So in order to do this, there's a couple of different lab experiments that will allow us to achieve the grain size distribution of a granular material or of a porous media type of material. So we have what's called mechanical sieve analysis, which is used on particles larger than 0.075 millimeters, or this is also 75 micrometers. And in this mechanical sieve analysis, we have what's called a dry sieve analysis, and we have what's called a wet sieve analysis. Now, in previous classes, you've studied a dry sieve analysis. This is where we shake a soil sample or an aggregate sample through a stack of sieves, and the topmost sieve has the largest opening and the bottommost sieve has the smallest opening. So that's a dry sieve analysis. We have not studied wet sieve analysis yet, okay? We also have what's called a hydrometer analysis. And this is used on particles smaller than 0.075 millimeters or 75 micrometers. Okay. Now, what's interesting is the number 200 sieve has opening sizes of 75 micrometers or 0.075 millimeters. So that size, that size that's a threshold between a mechanical sieve analysis and a hydrometer analysis is the number 200 sieve. So how do we do the mechanical sieve analysis? So again, as we mentioned before, we shake a dry soil sample through a stack of sieves, and the topmost sieve has the largest opening, and the bottommost sieve has the smallest opening, and then there's a pan at the bottom. So we should remember generally how to do that. We've done that before, okay? So let's talk about our procedure for calculations, okay? Let's talk about our calculation procedure. So the first thing you want to do is determine the mass of material retained on each sieve and in the pan. And we call these M1, M2, and all the way to MN and then M pan. The next thing you want to do is determine the total mass of the soil, okay, if you don't already have it. I said soil, I mean any material. Determine the total mass of material. Okay, so this is going to be M1 plus M2 plus dot 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 plus MN plus M pan, and we can call this M total, or the sum of all the M values. Okay. Step 3 is determine the cumulative mass of the soil retained above each sieve. Determine the cumulative mass of material retained above each sieve. So how do we do that? Well, we can say for the ith sieve, we'll have M1 plus M2 plus ... plus M sub I. Okay? And then step 4, we're going to say determine the mass of material passing each sieve by the following calculation. We would say M total minus M1 plus M2 plus ... plus M sub I. And then step 5, we're going to determine the percent finer for each sieve. Determine the percent finer than each sieve. And we do that, we typically call this F, and we say F equals 100% times M total minus the quantity M1 plus M2 plus ... plus M sub I all over M total. And then step 6, what we can do is we can plot F versus sieve opening, which is also called the particle size, on semi-log graph paper. And so the horizontal axis is on the log scale. And from that, we can later determine a lot of, very useful properties. So from this plot, we can determine the following. We can get the effective size, effective grain size, we call this D10. We can get what's called the uniformity coefficient. This is called C sub U, and that's computed as D60 over D10. We can get the coefficient of curvature, also known as the coefficient of gradation, and we call that C sub C, and that's equal to D30 squared over D10 times D60. And then we can also determine different percentages of constituents, which are, of course, gravel, sand, silt, and clay, according to different organizations. Okay. We can determine if the material is well graded or poorly graded. And then poorly graded materials can further be classified as gap graded or uniformly graded. Now that concludes our review of this topic.